In this video, we are going to do another improper integral type 1 example. So here is the example. I have this improper integral, and what makes it improper is the fact that one of my limits of integration is infinite. The bottom one is negative infinity. And I want to determine whether this integral converges or diverges, and if it does converge, then evaluate it. So to get started with this improper integral, I know I'm going to need to replace this negative infinity with a t. So I know I'm going to replace it with a t, and then I write everything else as it is, x, and then e to the x over 8 dx. All right, so I'm zooming it out a little bit so I can see more of the page here. So at this point, I want you to pause the video for just 30 seconds and see if you can identify, well, what technique do I need to use to evaluate this integral? 4, 3, 2, 1, pause that video. Pause it for 30 seconds and see if you can identify what technique do we use to evaluate this integral. All right, so hopefully you did that. Hopefully you paused it and thought about what technique do we use. It turns out we need integration by parts. So hopefully we're starting to get more and more comfortable with recognizing what technique to use when we see integrals like this. So with integration by parts, I need to choose what to let u be and what to let dv be equal to. And we're going to let u be equal to x because that has a really simple derivative. Du would end up being 1, but I have to make sure I write the dx next to this. dv is going to be all the other stuff in the integral, which is e to the x over 8. I can actually write that as e to the 1 over 8 times x. And then I have to write the dx next to it. And then the antiderivative of that, of dv, would be e to the 1 over 8x. But in front, or overall, I can think of this as I have to divide by this 1 over 8. And when I divide by 1 over 8, that's the same as multiplying by the reciprocal, which is 8. I would have to put an 8 in front. All right, so we are going to do this integration by parts. So let's apply this. And when we apply this, we will end up getting uv, so that is 8x e to the x over 8. I'm just starting to multiply these together. And then this is a definite integral. So on this part, I do have to put a line. Whoops, sorry. Ooh, undo that. Okay. So I do have to put a line and put a t and put a 4. And then minus my integral, have to put those limits, t and 4, and then v du. So that will be e to the x over 8 dx. So you might notice that I haven't put a limit in front of this. And that's because I'm going to end up, there's going to be enough steps in this problem where I'm going to evaluate the integral kind of like as much as I can, and then I'm going to put the limit in front of it just to save me some time so I don't have to keep writing the limit again and again and again at the start. I'll save that for the end when I'm ready to actually do the limit. All right, so what does this equal? So if we plug 4 into this, we will get 8 times 4 times e to the 4 over 8 is 1/2. And then minus what you get when you plug in t, which is 8t e to the t over 8. And then we'll get minus, and it looks like in my integral I forgot to write an 8. Yeah, it should have been 8 here with the e to the x over 8. So when I did v du. So if you caught that before, awesome. Okay, I'm just catching it now. Alrighty, so I'm going to do this integral. So the 8's still going to be there. And then antiderivative of e to the x over 8 is going to be 8 times e to the x over 8. So this 8 is the one that's still there. The next 8 that I wrote in the parentheses comes from when I do the antiderivative of e to the x over 8. All right, and now vertical line, and I got to plug in t and plug in 4. So when I have this minus sign in front of this integral, I have to be careful when I plug stuff in. So the way I'm going to think about this is that minus was in front of this original integral. So I'm going to put a bracket around this. And when I plug 4 into this, and when I plug t into this, that's all going to occur within this bracket. That's going to help me keep track of my signs. Okay, so what does this equal? So we get 32 e to the 1/2 is square root of e, and then minus 8t e to the t over 8 minus, and now 8 times 8 is 64, so we'll get 64 e to the 4 over 8, which is e to the 1/2. And then minus, when you plug t in, we'll get 64 e to the t over 8. Alrighty, so now we have plugged in all of our limits of integration. At this point, we are ready to take the limit. So now we would be ready to take the limit as, what's t going to? Negative infinity. So now we are going to be ready to do that. So I'm going to continue that at the top of the page. Alrighty, so I've just copied my expression from before. So then we need to take the limit of this as t goes to negative infinity. So the constant terms are going to be easy. They're just going to stay there. So what I need to worry about is the stuff that has t's in it. So as before, when I have a limit, first thing that I usually do is try to plug in. So if I plug into this, what I will get is I'll get negative 8 times negative infinity, and then e to the, it'll be negative infinity over 8, which is still negative infinity. So what this will give me is negative 8 times negative infinity is positive infinity, and I'll get infinity times e to the negative infinity. Alright, so I need to know what e to the negative infinity is. And if you don't remember, it's helpful to refer to the graph of e to the x. So the graph of e to the x, hopefully we remember this, but the graph of e to the x looks like that, where the y-intercept is the point 0, 1. So we want to know, well, what's happening as the input goes to negative infinity. So that is way over here on the graph as x goes to negative infinity. And as that's happening, e to the x is going to 0. So e to the negative infinity is 0. So we have infinity times 0. And as you would have seen before in the previous calculus course, and maybe in the L'Hopital's videos from the previous section, when we write the 0 here, this doesn't actually mean it's exactly 0. It just means we have that infinity in front. And by writing 0 here, it just means something that's really small. It's actually not exactly 0. Even from the graph, I can tell that, oh, the y values are not exactly 0. They're just really close to 0. So infinity times 0, infinity times something really, really, really small, is an indeterminate form. I can't tell what it is just by looking at it, but we've seen from the previous section that if we convert this to a fraction, we can do that and then use L'Hopital's rule, which I'm going to call LH. So our expression here was 8t e to the t over 8. How do I turn this into a fraction? Well, I can do it in two ways. I have to pick one of the terms that shows up here and bring it to the denominator. So if I were to do that with a t, we would leave 8 and then e to the t over 8 on the top. And when I bring t to the bottom, it gets reciprocaled. So it would become 1 over t on the denominator. Or I could also write that as t to the negative 1 on the denominator. I could also bring the e term to the denominator and leave myself with 8t on the top. And then on the bottom, I would have e to the negative t over 8 if I bring that to the denominator. So I'm going to put this in a little thought pyramid here. All right, and I also need to think about, well, what's going to happen with this term, the 64 e to the t over 8. Well, if you plug into that, you get negative 64. E to the negative infinity over 8 is negative infinity. So this is negative 64 times, we know what e to the negative infinity is. It's 0. So this whole thing is 0. So that last one's easy. Alrighty, so we are ready to continue with this limit. So this equals 32 over root e. I'm also going to take the minus 64 root e and move it more forward. So minus 64 root e. And then this very last term, we know that that limit is 0. So plus 0. And then I have this minus the 8t e to the t over 8, which I'll rewrite as a fraction, so I can use L'Hopital's. I'll get 8t over, bring the e part down, e to the negative t over 8. I could technically write it as a fraction either way, in either of these two forms. The second one just seems like it's going to be easier to do the derivative of on the top and the bottom, which is why I picked it. Okay, so, whoops, I forgot to write the limit in front of this. Let's go ahead and put that in. All right, so I need the limit as t goes to negative infinity of this entire expression. Alrighty, so what does this equal? So I know that this first part, 32 root e minus 64 root e, that's just minus 32 root e. So with this fraction, I need to now check, like, can I actually do L'Hopital's with this? And to do that, I need to see what form does it have. If I plug in negative infinity, the numerator is 8 times negative infinity, which is negative infinity. The denominator will become e to the positive infinity, because I'll get a double negative. So this is negative infinity over e to the infinity is infinity. And negative infinity over infinity is something I can use L'Hopital's on. So I need to indicate that I'm going to use L'Hopital's. So the way I do that is writing LH over my equal sign. And I need to do that to show my work. If I didn't do that, it's not fully showing my work. Okay, so now we do L'Hopital's. So I do the derivative of the top, which would be 8. The derivative of the bottom, which is e to the negative t over 8, times the derivative of the exponent. And the derivative of the exponent is negative 1/8. Okay, so from here, we are good to plug in. And plug it in, we get this equals negative 32 root e minus, and if I bring this negative 1/8 up to the top and I reciprocal it, we will end up with negative 64 on the top. On the bottom, whoops, I forgot to write my limit here. Okay, let's shift that over. So equals the limit as t goes to negative infinity. Okay, I got to put a LH over that equal sign. And now I'm plugging in what t is approaching. So I get to stop writing that limit in front. And on the bottom, I'll get e to the infinity. So this ends up being negative 32 root e. Root e, double negative becomes a positive. And then 64, this is 64 over infinity. E to the infinity is infinity. And 64 over infinity is 0. A constant being divided by a huge number is going to be really, really small. That's why it's 0. So we get negative 32 root e. And that's our answer. All right, so in the next video, we will do another example, but that involves an improper integral that has both an infinity and a negative infinity in the limits of integration.